Hello and welcome to another video. This time we're going to be looking at GPIO interrupts. On the EZ80 chip there are 3 ports, each of which has 8 bits. They can all be used for I/O operations. Each of those ports, and indeed each of those pins, can operate in a different mode. They might be a simple switch output to turn something on or off, or a straightforward input, such as when we attach a joystick. However, for this video we're going to be looking at interrupts, so we'll be using mode 6. This is where our code will receive an interrupt message whenever there's a change on one of the pins. That might be pressing a button or releasing a button, for example. If we look at the GPIO ports on our Agon, we can see that we don't actually have access to all of those pins. On port B we only have access to pin number 5. On port C we have access to all 8 pins, and only 4 of them on port D. Ports C and D are usually used for the joysticks. In our example we're going to be using port C and be using pin 0 and pin 1. We're going to be using a very simple circuit. There is a switch which is connected to ground and to the pin on the other side. The switch is also connected to the 3-volt supply with a resistor. This makes sure that the pin is tied high when the switch isn't pressed, but when we press the switch it brings it down low. This is the same format which is used on a joystick interface. So in its normal state it is high, and when you press a button or move the joystick, it turns it low. Here we can see our 2 switches. These are simple buttons wired to pin 0 and to pin 1. So if we take a look at our program, we can see what it's doing. We've got a title message first, and now it's waiting for something to happen. It's waiting for us to press a button. So if we first press the blue one here, we get a message come up that pin 1 was pressed, and if I let go we can see that it's released. And if I press the other one, pin 0 is pressed and released. We can press both of them in any order. You can also see below there's a binary representation of port C's bits. So let's take a look at some of the code. We've got the usual start at the top of our code here, which you've seen before. We have a few constants related to the GPIO ports defined here. And the setup is pretty much what we've seen before. We'll make sure that we're in interrupt mode 2. We'll clear the screen and hide the cursor. We'll then tab to a position and print the title first. The next 2 lines are the critical parts. We're going to set up the GPIO ports with the right configuration, and then we're going to start the GPIO interrupt listener. Our main loop is very simple. All it's doing is waiting to see if the escape key's been pressed, and it's doing nothing else. It just keeps going round and round until the escape key is pressed. So here's the critical part, the way we set up the I/O pins. There are 4 registers for each of the ports. There's a data register, a data direction register, and an Alt1 and Alt2 register. Each of those registers contains 7 bits, 1 each for each of the pins. If we look at the chart for mode 6, we can see that the data register needs to be set to 1. The data direction register needs to be set to 0, Alt1 needs to be set to 0, and Alt2 set to 1. And that's what we're doing here. We're setting up those values, and you'll notice here particularly the bits where we're dealing with bits 0 and 1. That is for pins 0 and 1. The next routine starts the interrupts happening. For each pin that we want an interrupt, we need to set up an event, and that means giving it a routine that will be called when that event happens. So here, this is the routine that we're going to call when this event happens. These event numbers are unique to each pin. So for port C pin 0, it will be 40 hexadecimal, and port C1 will be 42 hexadecimal. When we've finished, we can reset the GPIO so that it's back to normal. And so if we have a look at one of those interrupt routines, we can see what happens whenever there's a change in one of the pins. So for example, for pin 0, this is our event here. We'll disable any other interrupts while we're running this bit of code, and we'll store any of the registers that we're likely to use because we need to exit cleanly back to the program. We're going to read in the port and see what data's there. We'll also store that so we can use it later if we want. And for pin 0, we're going to check bit 0 to see whether it's high or low. And then we can make a decision based on that. And this is where we might call other bits of code based on the event happening. In this example though, I'm simply setting the address of a message that we're going to print to the screen. Once we've done that, we're actually going to make sure that the bits we're going to set are set and then output back to that port. This confirms that we've acknowledged the interrupt, we've dealt with it, and resets those pins ready for the next time there's going to be an interrupt. And next, we're simply printing the information to the screen about what was pressed and displaying that binary information of the port. So why would we use an interrupt? The main reason is that your code can be told straight away as soon as a button is pressed, and your code can deal with it. It also means that your code doesn't have to have routines which are constantly polling the port to see whether it's set or not. You can get on with other routines and just be told when there's a change. You can see how this can be applied to a whole joystick by using exactly the same technique.